Still talking about damped harmonic motion. Or we're transitioning from damped functions to damped harmonic functions. Harmonic motion, excuse me. So let's see, kind of get some definitions here. It said an object is in damped harmonic motion when the amplitude is determined by the function A of t equals k times the natural base raised to the power of negative ct. Well, we got to define some variables. Where y equals, substituting y for the amplitude over time, amplitude of time, ke raised to the negative power of ct times the cosine of omega, lowercase omega t, where c is greater than 0 and k is the displacement, c is the damping constant, and t is the time, and omega is the period. Wow. See if we can make some sense of this. All right, suppose a string on a guitar was plucked at 0.5 centimeters above its rest position with a frequency of 98 cycles per second and a damping constant of 1.7. Write a trigonometric function that models the motion of the string y as a function of time. Let's see, let's go back to what we said our formula was. We said that we've got an amplitude function of, let's go y equals, and then we'll substitute some variables here. K raised to the natural base of negative c time, then we got the cosine of omega time. Okay. All right, let's see. What was K? K was the, gotta look this up. That's the displacement. All right, that would be this 0.5 right here. So we got y equals, we're going to write this function, 0.5 times the natural base e, and c, what was c? That was the damping constant, so that's negative 1.7, and we're going to substitute x for t, okay, times the cosine. All right, so we got cycle, there's our damping constant. Then we got cycles per second, but we need the period. So we're going to have to figure the period. And let's see, so the absolute value of the period over 2 pi equals the frequency. And in this case, the frequency is 98 cycles per second. So let's see, our period then is going to be 98 times 2 pi. Let's see, 98 times 2, 98 times 2, that's 196 pi. That's our period. So the cosine of 196 pi times the time, which we're going to define as x. So there is our function. 0.5 times the natural base of e raised to the power of negative 0.17 x times x times the cosine of 196 pi, that's the period, x over, and which is time. All right, then the last thing, determine the time that it takes the string to be damped so that y is greater than or equal to negative 0.15, but less than or equal to 0.5. I think we need to head to the calculator. All right, well, here you see I put in our function. 0.5 times natural base raised to the power of negative 1.7x, where x is time, and our t for time, times the cosine of 196 pi, that was our period, times x, which of course is time. Let's take a look at our graph. Well, we definitely have a damped function. In fact, we could even put in the 0.5 times the natural base e raised to the power of negative 0.17x, and then the negative of that, but that seems like too much trouble. Now, what we're looking for out of this is where we see that we're oscillating between negative 0.15 and 0.15. So I'm going to go to the trace feature, and it just happened to be here. So you can see right here, so x is equal to 0.64 when y is equal to 1.31. It's kind of close to that 1.5. Let me go up here. We'll head down. Okay, and at 0, when x is 0.659, y is equal to negative 0.137. We'll go back up here. So at 0.64, well, that would be x is less than, or y is equal to, y is less than 0.13. Let's move down. Bottom kind of, let me get down here to the bottom. And here y is equal to, and when x is 0.65, so we're about between 0.64 and 0.65 on our x value. That gets us within the range of negative 0.15 and positive 0.15. So we might then conclude that somewhere around 0.65, 0.64 seconds, we're oscillating there in this damped function. Wow, it's pretty bizarre.